All right, welcome to video 3 for our lecture video series from Wednesday, March 15th, where we are going to look at an example of how to draw molecular orbital diagrams for a homonuclear diatomic that does experience sp mixing, meaning its sigma s and sigma p molecular orbitals are similar enough in energy that they can interact in such a way as to affect the energy positioning of our sigma s and sigma p molecular orbitals. Namely, our sigma p molecular orbitals are destabilized and our sigma s molecular orbitals are stabilized. So let's work through this with an example. Let's start by drawing the molecular orbital diagram of nitrogen and then determine the bond order. And then let's go ahead and get some practice in with determining if N2 is paramagnetic or diamagnetic based on the molecular orbital diagram that we draw. So let's jump into it. Let's draw our molecular orbital diagram for nitrogen. Let's see if I can draw a straight line today. Well, look at that. Looks like I can. Okay, I'm going to place N, and then N, and then N2 in the center. And then I'm going to write out my full electron configuration. So that is 1s2, 2s2, 2p3 for each nitrogen. Again, if you need to practice this, I would pause the video here and whip out a periodic table and justify for yourself that this is the electron configuration of nitrogen. And this means then that we have 3 molecular orbitals that are going to combine, our 1s, our 2s, and our 2p. And then we also have to account for sp mixing. So let's first look at the 1s. So the 1s is going to remain relatively unaffected because it is sufficiently lower in energy than my 2 sigma s. And it's really when I get to my valence orbitals that I need to watch out for my sp mixing. So now let's look at our 2s. So we know that because we have 3 or fewer valence electrons in our p orbitals, we know that we are going to need to use our sp mixing MO structure where our sigma s and sigma s star are stabilized and our sigma p and sigma p star are destabilized. So to show that, I'm going to show that my sigma s star is at a lower energy level than it would be if it were perfectly symmetric. So perhaps I should draw the sigma s star and then the sigma s. Nope, this is sigma s, not sigma s star. Getting ahead of myself. Sigma s star, and then show their position relative to the 2 s's that came together to make them. So we see here that this is a little bit closer to these two. And then our sigma s, just to really further exaggerate that here, is now even lower in energy. So Let's perhaps exaggerate this more. Okay, so here we see stabilization. This should be, I don't think that shows it that well. Sorry. You get to watch me struggle to draw today. Hope you enjoy the show. So let's do sigma s way down here, and then sigma s star, and then 2s. 2s, okay, I think this shows well enough that the sigma s is now lower in energy, as is the sigma s star. And now we need to look at our p's. So I'm going to, hopefully Notability doesn't freak out on me, move this all down, and hopefully now increase my energy axis. There we go. So I have looked at my combinations that came out of my 1s orbitals, which were largely unaffected by sp mixing. However, my 2s orbitals, when combined, created sigma s orbitals that were close enough in energy to sigma p, such that the sigma s and sigma s star have been stabilized. And then the difference here with our p orbitals, so we've got two p's that are combining now. So as a result of sp mixing, not only do we see the sigma s's are stabilized, but we also see that the sigma p's are destabilized, meaning that first up we have to create our pi molecular orbitals, because these are now more stable than the sigma p molecular orbital. And then we have our pi star molecular orbital. And then way up here, super destabilized sigma p star. Okay, so let's see here. We've got our 2p, 2p, and now we have our 2p creating our pi molecular orbitals. That's from our side-on combinations of our pz and py. And then we see above that the sigma p bonding orbital, because that has been destabilized as a result of sp mixing. We've also got our pi star antibonding orbitals. And then way up here, super destabilized, is our sigma p antibonding orbital. So sigma p star. Okay, so as a result here, we see that the sigma p is less stable than the pi orbitals. And we also see that the sigma p star is much, okay, let's see here. Let's be consistent here. So sigma p is at a higher energy than our pi. So the energy of sigma p is higher than the energy of our pi. And then the energy of our sigma p star has been super destabilized, so it is at an even higher energy state than our pi star MOs. So now let's fill in our molecular orbitals. So I've got my, starting down here, 1s, 1, 2 in each, 2s, 1, 2 in each, and then 2p, 1, 2, 3, 1, 2, 3 in each of my nitrogen atoms. And now it's time for us to fill this MO up. So I'm going to fill my sigma s star as a result of the combination of my 1s atomic orbitals. So I've got 4 total electrons, 1, 2, 3, 4. Now for my 2s, 1, 2, 3, 3, 4. And then I've got 1, 2, 3, 4, 5, 6 total electrons that I need to fill. So I'm going to fill 1, 2, 3, 4, 5, 6. And this is the MO diagram of nitrogen. So let's figure out the bond order for elemental nitrogen, N2. This is going to be 1/2 times the number of electrons in bonding molecular orbitals minus the number of electrons in antibonding molecular orbitals. Okay, so number of electrons in our bonding molecular orbitals. We've got our sigma s and sigma s. We also have our pi and sigma p, all containing bonding electrons. So I'm going to go ahead and count. That is 2, 4, 6, 8, 10. So I have 10 electrons in bonding molecular orbitals. And now going to my anti-bonding orbitals. I've got 2 in my sigma s star, and then 2 more in my now more stabilized sigma s star. And then I have none up here in my anti-bonding orbitals. So that creates a total of 4 electrons in anti-bonding orbitals. So that is 1/2 times 6, which gives us a bonding order of 3, which you and I would recognize as being analogous to a triple bond. And if we look at Lewis, we would see that N is triply bound to N with a lone pair on each nitrogen. So because we see a bond order of 3, we would expect there to be triple bond nature, except now just for MO theory, distributed over the entire molecule. Okay, let's ask ourselves if nitrogen is paramagnetic or diamagnetic. So we are looking at the highest occupied molecular orbital. So we're going to scan our molecular orbitals and find the one that is the highest energy that contains electrons. So it looks like it's going to be my sigma p. This is my highest occupied molecular orbital. And the question is, do I have unpaired electrons in here? And the answer is no. Electrons are all spin paired. So this means that N2 is not diamagnetic, but it is rather paramagnetic. Wait, no, I have that opposite. Diamagnetic. So what this means is that N2 would be unresponsive to a magnetic field, unlike oxygen, which would be responsive. So the main thing that you need to look out for in these MO diagrams where we do see sp mixing is you need to pay attention to how you draw your valence combos such that we see, again, our sigma S and sigma S star are stabilized, they're lower in energy, and our sigma P and sigma P star destabilized. So they are higher in energy. So higher in energy, lower in energy, lower in energy. All right. That wraps up all of chemical bonding. So now that we have constructed atoms using our quantum mechanical theory to create atoms according to their electron configuration and use that electron configuration to understand properties of atoms and elements, which allowed us to figure out how these atoms and elements combine to form either ionic or covalent compounds. And now that we know how covalent compounds in particular are formed using our simplistic Lewis model to our kind of more general valence bond theory model to now our more fully robust best model of chemical bonding molecular orbital theory, we have been able to make compounds. And now we are going to move into what happens when compounds interact with one another, which is what we call a chemical reaction. So we are building from the ground up in this class. So in video 4, I'm going to give you a brief introduction into chemical reactions, and we will discuss kind of some general types of chemical reactions and re-explore the notion of the law of conservation of mass and Dalton's atomic theory coming up on Friday.